Welcome back to the continuation of the tank design that we have previously presented in part 1. If we can recall what the tank looks like, it is 8 meters long by 3 meters wide, and it had a constant depth of 1500 millimeters. What else? It had a cantilever height above ground level of 500 millimeters. Now let's have a look at how we can model this. There are two ways of doing it. There's a simple way and the harder way. Now, simple frame analysis, or you can use the area element analysis. The 2D analysis using a beam on elastic foundation, Winkler's model. What is the problem with that? Well, let's have a look first at what it looks like. You can see here when the tank is full, a simple frame on a series of springs, and these springs can be modeled as align springs, which is the stiffness of the soil, the modulus of subgrade reaction. And we can see here the bending moment is within the slab. It looks like there's a pretty high bending moment in the slab because of the pressure of the water, and you know the water puts a pressure on the soil also pushes pressure back up on the water and causes the resultant moment to look like that. And we can see on this image here that the maximum moments is localized in the corners of the tank rather than the middle of the slab. So we have positive bending in the corners and negative tension, if you like, in the slab. Okay? Very nice and simple way of demonstrating that. However, we have a problem. What is it? If you think about it, a frame is basically two nodes, right, linked together via an element or a beam. But every node, I or J, has only 3 degrees of freedom. Okay, it can only move up and down, left and right, and rotate around the z-axis only. So that's the only information that we will get out of these nodes. In reality though, a pool or a tank or a 3D structure can move, every node can move in 6 degrees of freedom. Okay? So that's why we will move on to the next type of modeling, which we call the area element. What is area element? There are 3 different area elements: membrane, plate, and shell. Okay, an area element is basically a surface like this, or a plate, and it can take in-plane transverse loading, normal loading, and in-plane loading as well. However, the difference between the 3 is how it translates the loading into the nodes. Okay? Like a membrane, for example, translates the loading via axial forces only. And you will have a U1, U2, and U3 at every node. What does it mean? That with a membrane you can only get a translation in the U1, which is the X1 say, and U2, which is the Y direction, and 1 rotation R3, which is around the Z-axis. A plate though translates the loading, so when you apply a loading on a plate, it translates it via flexural only, via bending only, through until we get to the nodes. And what is the behavior of the nodes? The nodes can move only upwards in the U3. You will only have a Z direction movement. Okay. However, you can rotate the plate around the R1 and R2, which means you can rotate the plate around the X-axis and the Y-axis. But in terms of translation, it can only translate upwards. And hypothetically, they say, okay, using a solid slab, a slab on beams, a slab on columns, that's probably the case. You will not get a rotation around the U3. Unless, of course, we consider a slab on ground and the ground moves in 3 dimensions, and then we assign the soil springs with shear couplers, and then we have shear deformation, and then we'll get movements in all directions. Yes, that's a different story. So again, the membrane is axial forces and the plate only through flexural or bending forces, but a shell element can do everything, multifunction. It can, at every node, can move it has 6 degrees of freedom. So every node can go up and down in the U1, U2. It can rotate around the U2 and the U1, and also rotate around the U3, and also move up and down as well in the U3 axis. So, and that's why having a shell element can represent almost every 3D structure out there, especially a tank. Because when we have a tank and we apply a surface pressure on it, this is in 3D. Now this surface pressure has to be distributed into the panels, into the side panels, back into the nodes. And then the behavior of every node should be considered. So this is an example down here. I've shown where the tank is full. And you can see on the left hand side a picture here of a shear force, the contours of the shear forces in the shell elements. All these squares here are meshed. We meshed the whole slab so we can get more refined answers. And just imagine every mesh here has a node, has 4 nodes. So that means every mesh has 24 degrees of freedom. And just imagine how many degrees of freedom the whole tank would have. Okay, so that's why using stiffness method to work out the translation and the rotation at every node is probably the best way. And most of these finite element programs use stiffness method. What else? You can see here the tank is empty, a picture of the bending moment, or the contours of the bending moment. And the advantage of this as well is we can holistically see the structure. We can see what is happening. So not only one section of it, but the whole thing. So in this case, you have positive bending and then you have negative bending. And so you would know in what area we would need positive steel and negative steel. And it helps us to be more pedantic and provide a more cost-effective solution to our design. Last but not least, deflection and settlement. It helps us to assess the structural deformation of the whole project and the distress on the whole project. And you can see in this diagram the outline here is the initial position of the tank, and you can see the rotation here, or the deflection of the tank at this point. So it's good to the eye. You can assess everything step by step. So yeah, a tank or a 3D building, obviously a building isn't 3D, it is always best, and if we're applying even wind pressure on a building, it's best to use shell element. Now it's time to go to SAP, and hopefully we'll have some fun. Here we are at SAP. The first thing we do is say File up here and press New Model. We are given a lot of options. Again, we are not going to use a 2D beam or frame analysis. We could use this option here as a shell, but I would like to probably start with a blank project so that we can go through it step by step and learn it from scratch. The other thing here is the units to use. We will stick with kilonewton meters. There are so many units that the program offers, but we will stick with kilonewton meters, and C for Celsius temperature. But we won't use temperature gradient in this case. Okay, so we do that and press blank. We will see 2 windows and they're both in 3D. I like to keep one in 3D and the other one I like to change it to whatever I can. I mean, XY is looking at it from top view, or XZ or YZ. I choose XY. So I have one window here, XY, and one 3D. Now it's time to press define the coordinate system here. And then we press modify, show system. We are given the X, Y, and Z. The X ordinate in our case will be 8 meters. That's the pool length, and then we close it off at 0. The Y, the pool width, 3, and we close it off at 0. And then the height of the pool is 2 meters, and we close it off with 0 and press OK. And then press OK. Now you can see that it has drawn an outline of a cube, and here we need to change it back to X, say XY, and here you can see the plan view of the pool. Well, of the coordinate system that we have drawn. Now it's time to define our materials. So we press here define materials. We are given the default imperial names here, but we can change it. So 4000 psi is for the concrete, but we will change it. And we say modify materials. And we change it up here, and we may call it concrete. We will leave the density as it is, 23.5, and the modulus of elasticity is 24,000. So we need to change it. To change it, you come up here, press shift. You've noticed here that they've given us this value in kPa because we kept the program as kilonewton meters. This is how we initially chose our units. But to change it individually, we can do it. So we come up here and press shift, double click. And we can change the units here to Newton millimeters. Then delete this default value and write 24,000 and press OK. Great. The Poisson ratios are the coefficient of thermal expansion. They're all the same. We need to change the compressive strength here to 20 MPa. Again, they left it as kPa, but we come here, shift, double click, and then change this to 20 MPa. And press OK. Okay, is there anything else? And I think we look good so far, so we press OK. Here you can see the name concrete appeared, press OK. So we've defined the materials. Now we want to define the section properties. So we come up here again, define section properties. It's not a frame. We might do another video using a frame analysis, but it's not a tendon, not a cable, it's an area section. So we come over here, press area section, and we will see on our right hand the selection type. So we have shell, plane, or solid, but we will stick with the shell. And we will add a new section. I will call it slab. I will define two sections, one for the slab and one for the wall. So we have slab, it's a thin element, and the material is concrete, so we change it to concrete, and the thickness here is 0.2. Okay, and 0.2. Now the difference between a thick and thin element, a thick element will experience shear deformation. A thin element will, when it bends, plane sections will remain in plane. So anything really up to 300-400 millimeters is still considered as a thin element. Deep beams are considered as thick elements. Okay, press OK after that. And then we will define, add new section again, and we will define the walls. Okay, so we come up here, press walls, It is a thin element and it's concrete. We'll change this to the thickness of 0.2. Remember, we are using the units of kilonewton meters, so everything has to be in meters, okay? And we will press OK. Excellent. So we've defined now our shell properties, and we need to now draw it in. So there are several ways to draw it in. On our left hand side there's a free option where we draw in like we're drawing in an AutoCAD, or as a press of a button. Okay, so I will choose this one here, and we will start on the XY plane. So I come over here and then come here and press with the left click. As you noticed, it's red. So you can see here that on the 3D sheet, the 3D page, the red has been assigned. So I've drawn the first shell element of the pool. Now it's time to draw the walls. So I come back here and I go to the, let's say the XZ plane over here. This is 2 meters high by 8 meters wide. Again, you make sure that this is selected, but this time this is going to draw a wall, so we need to change this to walls, because we've defined it in the shell elements area before as a wall, so we change it to walls and come over here and click on it. If you noticed, it has drawn the first part of this wall. We need to now draw the wall behind it. The easy way to do this is come back into this plane and see those up and down buttons. We want to go a layer up, so we press up and then make sure that this is on walls and press here again. Now it has drawn the shell element at the back as well. Now it's time to draw the YZ plane. So we come over here, same sort of idea. And if you notice that when you go up and down a layer, the coordinate change y is equal to 3, means that y has moved 3 meters from the origin. Okay, this is the origin point, the global axis XYZ, and this is a reference point that we start from. Okay, we go to YZ, and YZ is basically 3 meters wide by 2 meters high. Come over here, make sure that this is on walls, click on it, and it has drawn this side where x is equal to 0. Then we go up and x is equal to 8 and press our button. It has drawn now the full shell of the pool. Okay, so we've done great so far. The next step after that is every single shell element or every single plane has a local axis. Okay, we need to see the directions of the local axis. So we come over here, make sure it's in the 3D view, and then click on the right button, this one here, click on it and go to area. This is what we're drawing, area, local axis. Right, we have the blue axis here represents the Z axis, the red axis represents the X axis, and the green represents the Y. What we want to do is make sure that all the Z axes are facing towards the pool so that we can orientate all these axes in one direction. So when we put the loads on, our program would know what our reference axes are. As you can see, this plane here has the axis outwards, and this plane at the back, the YZ plane, has the x-axis, has the z-axis outwards. Okay, we need to rotate these two to face the water inside. All of these planes have the right direction of the axis, and this one here has the z-axis going there. I tried to explain it better in this diagram here, if you can see here with me, this is what we have and this is what we're hoping to achieve. All the z-axis is facing the water, the pool inside, like that. And this will be the top face of the shell. And this will be the bottom face of the shell from the outside. That's the bottom face and that's the top face. We need to assign this orientation to the program so that we can be consistent with our moment and shear forces along the axis. Okay, going back to the program now. So what we do is we press on this arrow. That brings us back to default again. Press on this arrow up here and then come back, select on this plane and this plane. And then go to Assign, Area, and Reverse Local 3. Okay, so reverse local 3 axis, keep assigns in the same global orientation and press OK. You notice now that everything is facing one direction, which is the water in the tank. So you can see here the blue is facing that way, and for this plane the blue is facing this way. So we are now on the right direction. And the last thing we will do just before we finish off with this part, we will fill in our shell element. So we highlight everything here and go back to our check button and say Fill Objects and press OK. Here it has filled it in. And you can also do this in this plane as well. So we highlight it, click on it and say Fill Objects. Great. So here we have our shell element. Then what we do is mesh the whole structure. A good mesh for this would be say 0.5 meter by 0.5 meter. So we highlight everything again and we go to Edit, and then after that go to Edit and then we say Edit Area and Divide Areas. Then we come to this point here. We want to divide by maximum size, and we can divide this by 0.5 times 0.5 in the 1 to 2. This is along the edges from points 1 to 2 and 1 to 3. So we can divide that by 0.5 and 0.5. The lesser you make these, here you can see we have meshed the whole structure. The lesser you make these squares or the mesh, the more accurate results you get, but I can assure you that 0.5 meter by 0.5 meter for this is more than sufficient. Now you can see that the local axis has been assigned to every single panel that we have assigned. Okay, we will continue in the next video. Thank you for watching, and yeah, please share and subscribe in the meantime so other people can learn. Thank you and have a great afternoon.